Yeah, thank you very much. I would like to thank the organizers for giving me the chance to present our new material. I will talk about the prospects in the C=5 region and on the N=28 shell closure. So, well, I was asked to speak about medium mass nuclei, and I thought, well, what are medium mass nuclei? And thinking about yesterday's session, I decided, okay, the light nuclei are only the very light ones up to lithium. And considering that Kemina Misono will take in the heavy element session on nickel 54, I thought, so then the medium mass region must end at about nickel. So, and I picked here now two regions, which I would like to talk about, and everything else is in the heavy region, I guess. And so what I will talk about is, oops, oh, here we go. I will take the lower left corner, which is boron and carbon, actually. So I will talk a little bit about the traditional approach to measure different differential charge radii in this region, and our new approach for towards an all-optical determination of nuclear charge radii. And in the second part, which is the shorter one, I will shortly look on the N=28 shell closure and the transition here from calcium to nickel. Now, let me remind you quickly on what has been done on the lightest elements on nuclear charge radii, besides the hydrogen, so the proton and deuterium. This was covered excellently yesterday by Randolph. And also, if you look here on the charge radii on helium, so what is shown here are charge radii for the lightest elements, helium, lithium, and beryllium. And the error bars given here are those which come from the isotope shift measurements, whereas the gray regions are those which are due to the reference radii, which come usually from elastic electron scattering or muonic atoms. And you see that here in helium, there's practically no remaining uncertainty on this level here from the reference radius, which is helium-4. That is due to the very nice measurement on the muonic helium, recently published by the Bremer collaboration. So so therefore, helium-6 and helium-8 charge radii are just limited by the isotope shift measurements. It's different for lithium and beryllium, where actually the elastic electron scattering of lithium-6 and beryllium-9 are limiting the charge radii, particularly for the halonuclei. Just a reminder, halonuclei is the very interesting topic in this region, here shown for helium-6 and helium-8. So these are nuclei which have loosely bound neutrons or protons and which are far away from the nuclear core. Now, if we look a little bit further up and go to the boron, then there is a very particular nucleus here, boron 8, which is believed to be the best proton halo candidate. So here is a proton in a halo state. So we have a 1 proton halo nucleus, which has a beryllium-7 core and 1 proton. So this is similar to beryllium-11, which is a 1 neutron halo nucleus with a beryllium-10 core and 1 neutron around. So now traditionally we approach these charge radii by isotope shift measurements. And this has been laid out also yesterday in Gustav Parutsky's talk. So what we need is we need some theory to calculate the mass shift. And then we measure the isotope shift, and the difference between the two is proportional to the root mean squared charge radius. And we need then additionally the electron probability at the nucleus, so this field shift factor, in order to extract the change in the mean square charge radius. Now, this has been used in the beryllium, of course, to measure then the differences to the reference radius beryllium-9. And it will also be used and has been used in boron to measure the difference in charge radii between the stable isotopes beryllium-10, boron-10 and boron-11. But we will also use it then to measure the charge radius of boron-8, or the difference in charge radii between the stable and boron-8. Now, however, if you want to really in these cases, we need the reference radius. And as you have seen, the reference radius is often the limiting uncertainty then for the absolute nuclear charge radius. Now, since we have to do it here with a proton halo, it's that the proton halo size is actually determined by the difference in the charge radii between beryllium-7 and boron-8. So this gives you the best knowledge on the proton halo. But then we need reliable reference radii in both chains, and they should be on the same footing. And I will tell you in the following how we have measured the boron, the difference in charge radii between the stable isotopes, and how we want to measure the absolute charge radii in these two chains. Now let's have first a look on the boron 1011 measurement. So the differential charge radius with the so-called traditional approach. So the transition that we have investigated here is the P to S transition, 2P to 3S in the boron atom. And it has been done by resonance ionization mass spectrometry. We have used a second laser to ionize the 3S state afterwards above the IP and determine then, or determine then the created ions. So the transition here is about, we have started in the duplet P1/2 state. Transition wavelength is about 250 nanometers. So we have used a frequency quadrupled titan sapphire laser reference to a frequency comp, and the ionization was done with a frequency quadrupled neodymium laser. In order to produce an atomic beam of stable boron, we have used a graphite crucible, which was heated very high to about 2,600 Kelvin in order to generate a boron beam at about 2.1 kilometers per second. But that's just the thermal velocity. And the boron beam has then been, we had an aperture here in order to limit the transversal dispersion. And then the atoms enter an ionization region where they are superimposed with the resonant laser and the ionization laser. We create boron plus ions, which are then mass analyzed with a quadrupole mass spectrometer and detected by a channeltron. So relatively simple approach. However, what you have to make sure is, of course, that you have here really a right angle between the atomic beam and the laser beam. Why? Well, we have two things about that we have to care. If you look for the Doppler shift of the moving atoms and the laser beam, we have second order Doppler shift, which is on the order at this temperature of about 30 kilohertz. But we have also an angular dependence of the angle between the atom beam and the laser beam. And this is about 8 megahertz per millirad. So we have to be very careful about this angle. And therefore, Bernard Mars has had an idea how to measure this. Actually, we use a retroreflected beam and measure the spectrum with a single beam and with both beams at the same time. So this is shown over here. Let's assume we have the laser beam is not exactly perpendicular. We have an additional angle phi here between the perpendicular region and the laser beam, and perpendicular direction and the laser beam. And then now we have only the laser in one direction. Then of course we see the hyperfine structure of the boron 11 here in this spectrum. But this might be shifted to the real resonance frequency. Now we do a second measurement where we put a mirror over here and superimpose the retroreflected laser beam together. And now we have the opposite shift, because we have now the opposite angle with respect to the atomic beam. And so we see actually two resonances. And the center of the two resonances is then the real transition frequency. And this is shown here on this graph. Here we have now both lasers on, and you see clearly a shift between the two laser resonance, or the two resonances with one and the other laser beam. And from that we can calculate the center frequency. And with this approach, with respect to the frequency comp, Bernhard was able to measure the absolute transition frequency in boron 10 and boron 11 with about 2 orders of magnitude improved precision. Now, in order to measure the isotope shift between boron 11 and boron 10 is only a 20% isotope, so the statistic here was much worse. And Bernhard had the idea to measure then only the boron 10 only with one laser direction, but reference it then directly to the boron 11 measurement, which has been measured in both directions. But of course, what you have to take care of then is the fact that the boron 10 atoms are at a different velocity than the boron 11 atoms, since they have a different mass. But we know exactly how the thermal velocity scales with the mass, so we can use the square root of the masses of the mass ratio in order to calculate the respective frequency shift. And so we can do a direct comparison between the boron 10 and the boron 11, and from that we get the isotope shift between the two. Now, from the isotope shift, we can calculate then the change in the mean square charge radius. But what was necessary for that were the field shift calculation of the mass shift that has been done by Christoph Pachutsky. So this is a 5-electron system. So it was it was also some effort to calculate for the first time the mass shift with high accuracy in a 5-electron system, but this has been reached. And so we could extract the field shift, which is 8.3 megahertz with an uncertainty of 2 megahertz. And from the field shift factor, we can calculate then the change in the mean square charge radius. And it turned out that boron 11 is actually smaller than boron 10, which is similar as in the other chains in lithium or beryllium, and can be traced back to the halo to the clustering of these nuclei. In order to compare it with theory, we have now one problem, and that is that we have not a reliable reference radius for neither boron 10 nor boron 11. If what is shown here is the boron 10 charge radius on the x-axis and the boron 11 charge radius on the y-axis. And this here, F, given as F, is the result of electron scattering. You see that these results have very large uncertainties. And so we have no reliable reference radius, but from our delta R squared measurement, we can say that we can draw the line along which the real charge radii must be, where the real charge radii must lie on. And so this here would be delta RC squared equals 0. And this is the delta RC squared equals about minus 0.5. So somewhere on this line, the real charge radii of boron 10 and 11 must be located. And here are results from no-core shell model calculations from Robert Roth and Thomas Hüter, and Green's function Monte Carlo calculations from the Argonne group. And you see that they actually all lie along the approximately along this line, and their uncertainty bars overlap somehow within a little bit more than 1 sigma within our measurement. So now concerning the reference charge radius in boron, this is really a tragedy, as you can see on this plot. So here you have again the lithium and the beryllium absolute charge radii with their uncertainties. And here plotted are the uncertainties of elastic electron scattering measurements in red for boron 10 and boron 11, as well as from ionic atoms. And what you see is, again, the large uncertainties. This is actually a measurement from 1991, and this is one from 1966. So not much of an improvement considering the uncertainties. And the reason for these large uncertainties is the fact that we have a strong interference between C0 scattering and C2 scattering in the longitudinal form factor. You can see this over here. Actually, the C2 scattering is filling up the minima of the C0 scattering. And so we have here a relatively featureless form factor. And therefore, the fitting and the extrapolation towards Q equals 0 is harder than in other cases. All right. Now we need a different approach. Actually, let me just mention here, you see that the older measurements and the muonic atom measurements, they actually indicate that the charge radius of boron 10 should be smaller than that of beryllium 9. And we would have a crossing here actually, and this is unlikely. This value here is actually more likely than the one down here. And but this has to be clarified, and therefore we need a different approach. And this approach has actually been presented already yesterday by Christoph Pachutzky. The idea is to look in the helium-like systems, and he has detailed out this very carefully yesterday and presented calculations on the helium, on the neutral helium itself. That in order, if you can calculate the transition frequency in a system, in such a helium-like system, and for a point-like nucleus, and compare that to the real transition frequency, then we are hopefully very soon in a possibility to extract then the absolute charge radius directly from the transition frequency measurement. So this is the approach that has been talked about yesterday also by Randolph, of course. It has been used so far for hydrogen-like systems and muonic hydrogen, muonic helium, but and in the helium-like system there is still this small inconsistency that Christoph has mentioned yesterday between the transition frequencies, which rather fit well to the known charge radius, whereas the absolute level energies, there is a small offset, and this has still to be clarified. But we hope that with our approach, we can also contribute to this clarification. And so the idea here is, as Christoph presented yesterday, to measure transitions from the triplet S1 state in helium-like systems up to the triplet P state. And now, of course, in helium, you have a very long lifetime of the triplet S1 state. In lithium, this has been presented yesterday, also in the talk by Son. Here we have about, I think, 50 seconds lifetime of the state, but this goes quickly down with increasing set. So it's about 150 milliseconds only for boron, helium-like boron, and only 20 milliseconds for helium-like carbon. So we need also a very fast technique. You cannot easily do it in a trap, for instance. Yeah? So we need something that is an approach where you can measure quickly from the excitation in an of the metastable state until you really do the measurement. And an ideal approach for that is collinear laser spectroscopy. This here is the cover of a review of scientific instrument, where we have reported on our new apparatus here. No, it's not. It's already about four years old. We have completed it. The Koala setup at TU Darmstadt, which has now been extended actually in order to do measurements on helium-like system with an electron beam ion trap, which is still not here on this photo. This has been done last year in October. So we implemented this EBIS system, and Philip Imkram in his doctoral thesis has now started to do these measurements. He has also implemented this new switchyard here, which allows us now to have beams from 3 different sources and put them into the collinear laser spectroscopy apparatus here. Now, collinear laser spectroscopy is a quite simple technique. You just have to overlay an ion beam with a laser beam in collinear or anti-collinear geometry. So what we do is we produce here the helium-like systems in the EBIS. They are then extracted, directed here, deflected by about 60 degrees. And we can then introduce here a laser beam either in collinear direction or in anti-collinear direction. And here is a positive acceleration region. And then we have here the fluorescence detection, where we then can scan through the resonances and detect the fluorescence spectra. All right, now if we do the collinear excitation, we have the Doppler shift in collinear direction. So we have to have our laser frequency in the laboratory system to be higher than the reference frequency in the atom system, on the ionic system, whereas in the anticollinear it has to be lower. And we have now here a dependency on beta and gamma, which is the velocity. And since we do not know the velocity of the ions extracted from the EBIS very well, I'm already at 20 minutes. We have to measure both, measure absolute frequencies, and the product of the two gives us mu0 squared. Now, we started with carbon, actually. So carbon is an ideal test candidate because we have here very nice reference radius for carbon-12, which is shown here as well from elastic electron scattering, as well as from ionic atoms, and they agree quite nicely. And we also have measurements on carbon-13 and carbon-14 from both techniques. And so we have determined carbon. We have actually started with carbon since it is easy to produce in the EBIS. It has a transition wavelength of 227 nanometers, which we can easily produce with our Titan Sapphire system. We have no hyperfine structure, and we can then continue to carbon-13 and introduce the hyperfine structure. We're getting step for step a little bit more complicated. And also we have these very nice reference radii. So we have actually, Philip has measured in his thesis now, first the triplet P2 transition, which is the resonance is shown, or one resonance is shown over here. He has done a lot of measurements with systematic variation of the different, of all possible parameters. And you see a scattering here of about plus minus 10 megahertz. But of course, this includes all the variations of the different parameters. And as you can see here towards the end, by fixing some of these parameters and improving them, we could reduce the scatter. And we have now also measured the triplet P0 transition and the triplet P1 transition. And particularly here in the triplet P1, we have sufficient statistic, and you see a very small scattering now with the fixed parameters. And here we have lower statistical also to the lower transition strength. Now, the calculations for the helium-like carbon ions are in progress in Christoph Barutzky's group, and the C13 carbon measurements are in preparation in our lab. Now, stay tuned for further progress on this. I will skip over the next two slides, which actually shows a little bit the idea of progressing here. So I can shortly mention, so we start with the carbon-12 measurements, get the charge radius of carbon-12 and can compare it to the reference radii. Then we go over to carbon-13, get the carbon-13 charge radius. But what we can do additionally is we can use the traditional approach, measure the isotope shift between the two, and use then the mass shift calculations, and can also get delta R squared. And that allows us a consistency check. And a similar approach will be used then in order to extract the boron 8 charge radius. And there is actually, there are many more possibilities. And just to shortly flash the overview, so there are many checks possible and tests of QED, but I will skip over that one. We can discuss this later if it's of interest. Well, I thought this is a good point to stop for a pit stop and ask whether already some questions are there. I have four slides more than on the nickel because it's just one nice result I would like to show. Shall we make a break here? And do you already want to ask questions?
one question from Kay, please.
Hey, Wilfred, very nice talk. A quick question about the triplet S state. I don't remember well, but there is effect from the two-photon decay that reduces the lifetime of the metastable state. Can you comment on that? Oh, I mean, you obviously saw the resonance for the carbon.
Well,
So
the triplet S state is actually limited in the lifetime by the increasing amount of the M1 transition, I think.
Mm-hmm.
And this rapidly increases with that. I think it's set to the cube. And that brings the lifetime very, very quickly down.
I think, yeah, the two-photon or the M1 decay rate is relativistic M1. That goes Z to the 10, amazingly fast.
Yeah. Okay.
Thank you.
All right. Any other question on this part? Then let me just show 4 slides on the n equals 28 shell closure. What you see here is the kink at magic neutron numbers, which is well established. We have discussed this also in Paul Gert's talk yesterday, here for the lead region. But you see it everywhere. Yeah, every magic neutron number, classical magic neutron number above 28. It's not there at n equals 20, and it has also not been shown on any lower ones. Neither on the new magic numbers n equals 32 or 34, which are believed to be new magic numbers in the calcium region. We have also discussed yesterday that explanation for this might be pairing and/or spin orbit. And you see that in all cases, you have very similar behavior above the shell closure, whereas below shell closure, it's different. Yes, you have quite diverging it here in n equals 28, also in n equals 82, and more similar in 176 and at 50. Now, so far, doubly magic nuclei are on all are only here measured for in the neutron rich region. There is no doubly magic nuclei in the neutron deficient region, and actually the only place where it is easily possible is the n equals 28 region, where you have calcium 48 on the one hand side, and then above at nickel 56. So here it's easily reachable, and now, but there's still quite a difference between the two shell closures over here, which can be seen if you look on the energy of the first excited to plus state. According to that, if you go along the calcium chain here, which is shown over here, you have clearly high energies for calcium 40 and calcium 48. Then you go up here along the isotones. There again, you have for 48 and 56 nickel, you have relatively high values. And along the nickel chain, you have also high values for nickel 56 and nickel 68, and in particular nickel 78. However, the transition strengths, the BE2 value, this should have a minimum for a magic number, and you see this is well the case for calcium 40 and calcium 48, but much less for nickel 56. And it's quite well known already that nickel 56 is a much less strong shell closure than the other nuclei. And now it's interesting, of course, to see how this kink behaves if you go from a doubly magic neutron-rich nucleus to a doubly magic neutron-deficient one. And this has been recently measured at MSU, so I will not talk about the setup here. I'm quite sure that Kay will talk about it tomorrow. So let me just show the spectra of the nickel isotopes. So here, nickel 60, nickel 58 are stable, and then nickel 56 down to nickel 54 has been measured, including nickel 55. And if we now extract the charge radii, they are shown here with the black points and the uncertainty region. And 57 nickel has not been measured, so therefore here we have this straight line, this dotted line between the two. And we have here results from density functional theory with SV-min and a finance functional. Actually, and we have also in medium configuration interaction. So this is a no-core shell model-like calculations in this region, and from valence space in medium similarity renormalization group calculations using the N2LO SAT interaction as well as the delta N2LO GO interaction. And for each of the three few particle approaches, we have or many body approaches. We have shown here the best interaction, and you for the trend along the charge radius, as you can see here, and they all reproduce somehow the trend. The absolute charge radius is best represented by the N2LO SAT with the valence space in medium calculations, and but the others agree within the uncertainties. Here for nickel 56, we have shown the different approaches, the different interactions for the different many body approaches. Now let's have a look on the kink between calcium and so this is the kink for calcium and for potassium actually, and now we compare that with the kink in okay, and now we can. So we're already introduced by Burgert yesterday. We can use the so-called 3.2 neutron difference in order to establish to have quantity for this kink strength. So it gives in principle a change of the slope at the magic shell closure, or at the shell closure. And here you see this value for potassium and for calcium, and for manganese and for iron. And you see for manganese and for iron, this is larger due to the increasing quadrupole correlation in these nuclei. And the question is, what is the kink strength here now for nickel? And this is the result for nickel, and you can see that it's very similar to calcium. And actually, if you calculate the delta 3 to n, then it's almost exactly the same value as in calcium. And this is also quite nicely reproduced in all theories. So the value itself is different for the valence space calculations, but that the two are the same is also a result here. And so this clearly shows that the strength at the kink is, the strength of the kink is not an indication for strength of a shell closure, because that the shell closure at nickel is much less than at calcium 48, I think should be clear. So even though n equals 28 is only a weak shell closure, the strength of the kink is identical to calcium. But that is something I would like you to carry home. So this has been recently submitted to Physical Review Letters. And with that, I come to the conclusion. Yeah, I leave that for you to read. But finally, I would like to thank my whole group for the many results that they have produced during the Corona pandemic and before, but also particularly the many collaborators at Becola, at Argonne, where I only have few named, and also all the theory colleagues which have contributed to these results. Thank you very much for your attention.
Thank you very much for this very nice presentation. We have time for questions from the audience. So if you have questions, please raise your hand and unmute yourself and ask your question. I also remind you that we have an additional session at the end left open for discussion. So Christoph, first question.
Yes, Wilfred, so I forgot what was this last nucleus you have been describing, but in all this heavy nuclei, for me it is heavy, you have to include also nuclear plausibility to extract the charge radius. So are you doing so?
Well, we need somebody who calculates it.
Yes, so it means that you present the result for charge radii without verifying the magnitude of nuclear plausibility. I would say this is important. This would be important, or this is important to check it. To my opinion, it is not a difficult problem because electric hyperpolarizability, you mentioned about nuclear phases in your list, so they should be able to calculate. This is relatively simple.
I would expect that we have, well, you know, the
polarizability
of
deuterium,
lithium.
Even for deuterium, it was significant. So
but have a look at the polarizability, I think, of lithium 11 or beryllium 11, where you have included it, is much higher than the polarizability of a C12 nucleus. For boron, it's certainly different for boron 8. But
but for calcium, which you presented?
Pardon, for calcium?
Yes.
I don't think that the nuclear polarizability for here we have a valence electron with a very small probability of being at the nucleus, and we only measure the isotope shift and the polarizer. I don't think that at we have here an accuracy of about 4 to 5 megahertz. I don't think that it plays a role at this level.
It is not at this accuracy. Okay, thank you.
Okay, more questions? So if not, I suggest to move on to the next.
Yeah, I was going to. Sorry, I have my hand. But yeah, just a quick question. Yeah. So Wilfred, for boron 8, so you will do that with a highly charged ion as well.
No, actually, boron 8 we will the measurement of boron 8 itself will be done on the neutral system.
Okay.
But they will take only the boron 8 difference in charge radius and refer then to the boron 10 or 11, which we have measured absolutely.
Okay, I see. Yeah,
but then we have, with the optical determination, we have both the boron and the beryllium on the same footing.
Yeah, I see.
This is different with electron scattering, since you have this very strong C2 contribution, which you don't have in beryllium, so they will have totally different systematic uncertainties.
Yeah. Thank you.
So there are a couple of more questions.
There is one more question, yes. Leonid?
Hello, Wilfred.
Hello, Leonid.
I would like to know, did you take into account mass shift constant in nickel conical?
The mass shift?
Mass shift, yeah.
The mass shift, yeah. We extract actually the mass shift here from a King plot. So we have the known charge radii of the stable isotopes and perform a King plot, and from that we can separate the mass shift and field shift.
Okay.
Okay, yes. Our topic is searching for light bosons with King and second King plots. And as with Wilfred, I was a little surprised to see this in the medium mass section. Perhaps the reasoning is that King plots are normally used for medium or heavy nuclei, and the news, what is new about this talk, is that they can also be applied to light nuclei. And in particular, I looked at lithium plus, and you can do this by taking second differences to form a second King, or what you might call a super King plot. And so that in a nutshell is my talk. And I just wanted to mention that two of my collaborators, Victor Martin and Javier Dinsa, worked on this project as undergraduate students as a fourth-year project. So as an outline, after an introduction and motivation, I'll just talk briefly about what is a King plot for those who don't know. Searches for new physics due to an electron-neutron interaction. So this will be the motivation, looking for evidences of a physics beyond the standard model, definition of a second King plot, and then a comprehensive search for the optimum King plot in lithium plus, and then finally results and conclusions. So the motivation, as many of you are aware, that high accuracy atomic physics measurements at low energy have the potential to complement or even extend what can be learned from high energy particle experiments. And in fact, a new edition of the Handbook of Atomic, Molecular, and Optical Physics is currently in preparation. There will be sections in this on searches for new physics, and particularly from the New South Wales group, Victor Flambaum, have made important contributions to King plots. And there'll also be a chapter by Mariana Safronova, who will be speaking later on, as today, I believe. So King plots, fundamental precisions are made possible by very high precision measurements of isotope shifts. Optical clock transitions are now at the few hertz level, and there's even talk of millihertz measurements by use of coherent optical spectroscopy. So there's the potential in the future for very accurate isotope shift measurements. And in a recent King plot measurement in ytterbium may indicate evidence for an interaction beyond the standard model. Other measurements have been done in calcium and strontium. Analytical methods have been extensively developed by the New South Wales group. And the goal of this work is to extend King plot methods to light atoms where second order mass polarization effects are important. And this is what limits the applicability to light in the past to light atoms and ions is the contribution from second order mass polarization, which it produces a systematic deviation normally in King plots. In the case of lithium, all 5 isotopes from lithium-6 through lithium-11 have been extensively studied and nuclear charge radii determined, in fact, by Wilfried Nörtershäuser and his group have made dominant contributions to this. And on the theoretical side, high precision theory is available, as we saw in the talk yesterday by Wei Sun. This talk is based on this recently published paper published as a FISRA A letter. And so what is a King plot, first introduced by W.H. King, 1963, provides a systematic method to look for systematic trends in isotope shifts. The basic idea is to partition the total isotope shift into a mass shift and a field shift due to nuclear size and structure. And so if I and J denote 2 atomic states and A the isotope shift, then it can be expanded in powers of the ratio of the electron reduced mass to the nuclear mass, which is, for lithium, it's about 1/10 to the minus 4. The leading term Uij is the contributions to the energy for infinite point nucleus, including all relativistic and QED effects. But we don't have to know those because they cancel when you form the King plot. And similarly, the Vij term includes these normal and specific mass shifts, again, including relativistic and QED. And then the Wij term, this is the second order mass shift, which would normally cause deviations in a King plot, and so we can get rid of it by taking second differences. And then the last term, the field shift term in lowest order, is proportional to the mean square radius, and the Cij is the coefficient that is just the electron density at the nucleus. It's a first lowest order approximation. So the isotope shift between 2 different isotope shifts then consists of the, for A and B are now 2 different isotopes. We have the mass shift, the field shift. And if we divide by the difference in masses, then the U term cancels, and we're just left with Vij plus the Wij times the masses. And so this is what a King plot looks like, just as a rough idea. You plot one transition on the vertical axis, another transition on the horizontal axis for a sequence of isotope shifts. So for example, the first dot is the lithium-6 to lithium-7 isotope shift, the next one 7 to 8, next one 8 to 9, and so on. They should all lie on a straight line. And so if a deviation from a straight line would then indicate some new physical effect. So that'd be a kinky King plot. So for an ordinary King plot, you then need 4 isotope shifts. If you take second differences, you need a 5th isotope. And so lithium is the first case where that would be possible because we also have lithium 11. So just going back, so if we have a 3rd isotope shift, then and if we neglect the W term, then we're just left with the matrix elements of the delta function. So it's just the C terms, which is just the ratio of the electron densities at the nucleus. So this is the ideal case where there's no additional contribution. If the isotope shift between different isotopes A and B is then if we divide by let's see, yeah. So I've already done this. So searches for new physics. So there are at least 3 sources of nonlinearity. First, for light atoms, the second order isotope mass polarization term contributes. There are higher order corrections also to the field shift term, but the third is an additional electron-neutron interaction due to exchange of light bosons beyond the standard model. And so it's this item number 3 that we're particularly concerned with in this talk. So if there is the existence of a new light boson is a potential candidate for dark matter, and since it depends on the number of neutrons in the nucleus, you should see a progressive change as you go from one isotope to the next. And so you could postulate a Yukawa type potential proportional to the number of neutrons, and the distance scale is inversely proportional to the mass. And so if it drops off too rapidly for a heavy boson, but for a light boson, it's the distance scale would still be within the range of the electrons, and so you could expect to see a difference. So the boson must be light because otherwise the range is too short. So the useful mass range is therefore from 0 up to about 10 keV. And if present, it would produce a kink in the King plot if all the other effects have been properly taken into account. So if there is an additional term, if we ignore for now the W term, and let epsilon denote the difference in matrix elements for the Yukawa potential between the 2 different atomic states, then the King plot contains, if we go down to the bottom, the change in slope in going from one isotope pair to the next would then contain this additional term in the depending on the differences of the epsilon matrix element. But of course, this doesn't work for lithium plus because the mass polarization term is too large. The cure is to take second differences. And so I won't go through all the algebra for this, but by taking second differences, you then eliminate the W term. So here's the modified King coordinate. And so now when we take differences, the W term cancels. And again, we're just left with a slope that depends on the ratio of the electron density at the nucleus for the atomic states in question. And so again, you can then introduce a hypothetical additional term depending on the matrix element for the boson, and the multiplying factor n then depends on the neutron number for the isotopes A, B, and C, and this is 0 if the neutron numbers are all equal. So this only contributes if the so this is why it can be applied to light nuclei. There's no particular advantage in a heavy nucleus because the effect only depends on the change in neutron number, not on the absolute number. But again, you obtain a separation into a term that depends on the ratio of the electron densities and the matrix element of the hypothetical Yukawa potential contributing. So if this is there, then the ratio would deviate from a constant straight line. And so this is so if isotope D is replaced by a fifth isotope, then you would see this change in slope. And this is the factorization into a part that depends on nuclear properties and a part dependent on the electron wave function. Sensitivity to new physics, what is common in the literature is to assume a 1 Hertz uncertainty in each of the 4 isotope shift measurements required to make a King plot, and then to equate to calculate the sensitivity, to find what change in slope would correspond to the 1 Hertz uncertainty in the measurement. So this then determines a figure of merit for different transitions. So we look at different transitions and see what the sensitivity is corresponding to a 1 Hertz uncertainty in the measurements, just as a standard reference. I'll just talk briefly about the calculations themselves done in Hiller's coordinates. So we do high precision calculations, and we've extended these up to n equals 10. So these are new variational techniques that we've developed that work for high-lying Rydberg states. In fact, we're going higher than that. We're up to n equals 15 now. So by doubling the basis set to produce 2 different distinct distance scales, and including explicitly the screened hydrogenic term in the basis set, because this accounts for the first several figures in the energy. So it's numerically advantageous to do that. And then optimization of the nonlinear parameters to produce high precision wave functions for high-lying states. And so we've done calculations for all states up to n equals 10 and L equals 7, K state, the 10K state. The transformation to center of mass plus relative coordinates is what introduces this mass polarization term, in addition to the ordinary kinetic energy and Coulomb terms. Is this additional mass polarization term that, and if this contributes in second order, you then have, in addition to the normal isotope shift and the first order specific isotope shift due to the mass polarization term, is also a second order contribution. So this is where this W term comes from, the second order term. It's a second order mass polarization. Also, of course, there are mass scaling terms of that same order. I just wanted to mention that there's an asymptotic expansion for these matrix elements of the delta function. So the whole theory rests on evaluating the electron density at the nucleus. And for high angular momentum states, there's a very simple asymptotic core polarization model that you can use to calculate these matrix elements of the delta function. In fact, this is not that widely known. This comes from a paper, 1992 paper, where you can write the matrix element of the delta function in terms of this leading term is the part. This is state independent, and so this cancels when you take differences, and so you're left then with it's like a core polarization model. The second term depends on the 1 over x to the 4. X is that's the coefficient. X is the coefficient or the coordinate of the Rydberg electron, and here's the nucleus and the inner 1s electron that gets polarized by the outer electron. And so this, in fact, produces very accurate results. And in fact, for L bigger than 3 or 4, this polarization model is so accurate that you don't really need to do variational calculations anymore. It's perfectly adequate. Interesting feature is that the 5-10 state is almost equal to the 6-7. That's where L equals 6, N equals 7. So there's this accidental cancellation that occurs here, which suppresses the contribution from the nuclear finite nuclear size. Also, the finite nuclear mass works very well. So let's look at some results. we've done calculated all possible King plots for lithium plus up to n equals 10 and L equals 7, and counting both singlet and triplet states, there are over almost 14 million possible King plots. And so we ran our computer program for all 14 million, assuming a 1 hertz accuracy for isotope shift measurements in order to find the ones that are most sensitive. And so here are some results. These are the slopes of the K1, K2, and K3 are the slopes of the King plot, and K1, 2, and K2, 2. These are the second King plots formed by forming second differences. In the infinite mass case, these are all equal. All the slopes are equal. But when you add the mu over m squared term, this is the second order mass polarization. They're quite different for the ordinary King plot to give totals that are completely different for K1, K2, and K3. So these are the ordinary King plots. But for the this variation is completely eliminated by taking the second differences to get slopes that are almost equal. Another important feature of this that emerged as I did the calculations is that the nuclear radius uncertainty is also strongly suppressed by about 4 orders of magnitude relative to an ordinary King plot. And so this, in fact, this is one of the things that limits the applicability of King plots is the nuclear radius uncertainty. And so this could be applied to any sequence of isotopes, not just lithium, but medium and heavy isotopes as well. And these are the uncertainties in the deviations in the slope due to the 1 kilohertz, 1 hertz assumed experimental uncertainty. So these are the most sensitive transitions. They all so gamma. This is gamma is the parameter controlling the range of the Yukawa potential, and the conversion factor is if you multiply this by 11 keV, that takes you to the corresponding mass. And so the most sensitive ones are the at least for small gamma are the ones beginning with n equals 2 up to n equals 10. This kind of represents an asymptotic limit. So 9, 8, 7 are only slightly worse than this, and so we're approaching an asymptotic limit. Of course, these transitions are in the vacuum ultraviolet, so these would not be easy experiments. But I'll talk more about that in a minute. But then as gamma increases, the optimum rapidly lose sensitivity, going from 10 to the minus 15, and then by the time you get out to 1, it's 10 to the minus 13, and then for large gamma, it becomes very short. It becomes just like a delta function potential then, and so it just disappears into the nuclear size correction itself. For the case of oh, by the way, so these are like exclusion. So the last column, this is the coupling constant that determines the strength of the boson interaction. And so these are exclusions. So any value of this bigger than this number could be detected. If it's smaller than this, then you wouldn't see it. Much more easy experiments would involve the n equals 2 states. And so these are the possible King plots for the n equals 2 states, and in comparison with the one for the most sensitive one, you can see there's a loss in sensitivity of a factor of between 10 and 20. So these would be much easier experiments, but about 10 or 20 times less sensitive to a light boson. And so this is represented in graphical form, the exclusion plots. The solid black line here represents the current results for lithium plus, the second King plot. So anything above this could be detected. See, so below wouldn't see it. And in comparison with other methods, the dotted ones, these are the ytterbium plus exclusion plots from the Berengut paper. Hydrogen to deuterium isotope shift is shown here, G-2. And also there are astrophysical limits from globular star clusters and searches for a fifth force, which also, these would actually be more sensitive, but they're strongly model dependent. And so it's highly desirable to have an independent check based on laboratory measurements rather than astrophysical ones. And so this would be, so an experiment in this region would still be of interest. So in conclusion, we've defined and tested a second king plot that eliminates second order mass shifts as needed for light ions such as lithium plus, but of course the method can be applied to any sequence. They don't have to be light, but what is new about this is that you can do king plots for light nuclei. We've carried out high precision calculations for all states up to n equals 10, L equals 7 to identify the ones most sensitive. The sensitivity is about the same as recent measurements for ytterbium plus, up to about 10 for masses, boson masses up to 10 keV. The optimum king plots, of course, as I say, these are in the far vacuum ultraviolet, around 90 nanometers, but the experiments within the n equals 2 manifold would still be of interest. And I'm still looking at the implications of this accidental cancellation for this is the 7i to 10h transition because of strong cancellation of the field shift. And from the asymptotic expansion, you can see that this is approximately independent of Z. So this cancellation would apply for all of the light ions. The same method can be applied to helium and other light helium-like ions, and in addition to the heavy ones. And some online resources are available at my webpage. So I'll stop there, and thank you for organizing a very interesting workshop.
Thank you very much for this very interesting presentation. And the floor is now open for questions. So please raise your hand, unmute yourself, and ask your question. And also there will be time for discussion at the end of today's overall session. So questions from the audience? Chenji?
Hi. Hi, Gordon. Yeah, very nice talk.
Hi, Jen.
Hi. So I have one question. Can the nuclear wave function or nuclear excited states enter or contribute to the king plot?
The nuclear wave function, is that what you're asking?
Yeah.
Well, that would contribute. I mean, the leading contribution is just the finite nuclear size. And so to the extent that it doesn't contribute directly, at least in lowest order. I mean, I guess as Christoph discussed yesterday, nuclear excitations and nuclear polarization would contribute. One of the possible contributions is, in fact, the nuclear polarizability. But to the extent that this can be included as an effective nuclear size, it's a common factor for all states, and so it would cancel. So again, I mean, this is the beauty of king plots. Just you have so much canceling, so many systematic effects just cancel, and so to the extent that nuclear polarizability can be regarded as an effective nuclear size, then it doesn't contribute.
I see. Okay, thank you.
Yeah, but that'd be the leading contribution from nuclear structure.
Great. Thanks, Ronald. Thanks for having me. Thanks for coming, everybody. Sorry we couldn't be together in person, but it's nevertheless exciting to come talk to you. So like Ronald said, I'll be talking about fundamental symmetry violation searches with molecules, and my goal, since it looks like I'm the first of several molecule talks, that I'm going to give an overview, but with an emphasis on some selected current trends, some of which you'll hear more about later. The quick summary of the motivation for why we want to do these measurements is that the baryon asymmetry suggests new undiscovered CP violating physics, so the fact that the universe is made out of matter but not antimatter. Whatever this new physics is will generically lead to CP violating electromagnetic moments in regular matter, standard model things like particles in nuclei, so things like electric dipole moments, something like an electric dipole moment in nuclei called a nuclear shift moment, and magnetic quadrupole moments, which violate T and P and CP symmetries. And by searching for these moments, that allows us to probe for new physics at pretty high energy scales for this undiscovered symmetry violating physics. And these effects are all enhanced quite significantly in molecules, making them a good platform to search for this physics. So if you'd like to measure an EDM, the basic idea is you can use the fact that an EDM experiences a torque in an electric field. The searches for these other moments are similar. The EDM is sort of simplest to understand and visualize. So the experiment is you take your particles, you initialize them in some known spin state, you let them precess in fields, you measure the precession angle, and then you repeat many times because you're looking for something very small. The observable here is given by the product of the EDM, the size of the field that the particles are precessing in, and the coherence time, the interaction time. So you want those things to be large. And atoms and molecules have extremely large fields. They can be as large as 100 gigavolts per centimeter for very heavy species, where these effects are relativistically enhanced. And that should be compared to the largest field that can be created in macroscopic volumes in the lab of about 100 kilovolts per centimeter. So you get a 10 to the 5, 10 to the 6 enhancement of the field by using an atom or molecule. And the general idea is that these CP violating moments of the constituents of the molecule will cause symmetry violating energy shifts in the molecule. So for example, if you're looking for an electron EDM in some molecule with a valence electron, whether that electron's spin and dipole moment are aligned or anti-aligned relative to the internuclear axis, which sets the field, you'll get some splitting between these two states, which should nominally be exactly symmetry projected degenerate. And again, it's a similar idea for nuclear shift moments and magnetic quadrupole moments, even though this sort of simple picture of something experiencing a field is a little more complicated when you start thinking about the nuclei. The end result is pretty much the same. Molecules are very polarizable, especially compared to atoms, and that tends to give them around a factor of 1,000 or so intrinsic sensitivity increase compared to atoms. But nevertheless, atoms set the best electron EDM limits until not that long ago, just because molecules are very complicated. Doing even basic things with them can be very hard, and atoms are still the best in a number of other areas, but there are a lot of molecule experiments coming online in the next several years, which hope to be competitive with these atom experiments pretty broadly. There are 3 molecular EDM searches that have produced limits on the electron EDM. So far, just the electron EDM. The YBF experiment at Imperial College in a pulsed supersonic beam, which was the first molecular experiment, EDM experiment, to beat the sensitivity of the best atom experiment, which was thallium. The ACME experiment a few years later, the first generation, and then the second generation a few years after that, which used spin precession in a cryogenic molecular beam, and is currently the most sensitive limit on the electron EDM. And an experiment at Gila and Boulder using hafnium fluoride plus ions, so doing spin precession in an ion trap where they benefit from very long coherence times from trapping their species. These experiments collectively indicate a factor of about 100 improvement in EDM sensitivity in about 10 years. So it's moving pretty quickly. Each of these experiments is being actively upgraded and have demonstrated a number of improvements. So they expect to release improved measurements in the next year to couple of years. Of course, atom technology is also advancing very rapidly and excitingly, but I'm just going to focus on molecules for this talk. So interpreting these, these unitful constants, these E electron charge centimeters, that might not be a super meaningful constant. So, but a way we can interpret those is by asking, we're looking for new particles and forces. What sort of mass reach do we have for some new particle or force causing that would give rise to limits that are that these experiments would have seen? And a nice thing about these EDM experiments is that they're effectively standard model background free, meaning that at least for the next several orders of magnitude, we don't expect to run into anything from the standard model that could give us a signal. So it should be a pretty clean probe of beyond standard model physics. And so you can make a simple assumption that you just have some new particle with a mass m that has a CP violating coupling of order unity. And that would tell us that, at least for this sort of very generic model, these experiments are probing one loop effects at the tens of TeV scale and two loop effects at the several TeV scale. Of course, you can come up with specific models that have much higher mass reach, but this is a fairly generic mass reach for these experiments. But an important thing to remember is that because there are multiple sources of CP violation in atoms and molecules, you need multiple experiments to disentangle the effect. So to get robust limits, but eventually when these experiments start measuring things to actually figure out where is it actually coming from. For example, these electron EDM experiments are actually sensitive to both the electron EDM and a scalar pseudoscalar coupling between the electron and the nucleus. And with one experiment, you can't tell what it's coming from. You'd have to do more than one experiment. This is especially true for hadronic CP violation searches, where there are many, many sources. And so we need multiple experiments looking at these using different systems. And there's also a really important role of theory here. So making this connection, there are actually a lot of steps to go from some measurement to some new physics limit. The first step is you just have to figure out how sensitive is your atom or molecule to these effects? How amplified is the electron EDM or a nuclear shift moment? And so that requires very sophisticated atomic and molecular theory. For nuclear moments, there's an additional level of complexity to connect these collective moments to underlying sources like strong CP violation or new CP violating nuclear forces. So that requires nuclear theory. And then to go from these underlying observables to new physics theories, you need high energy theory. So this research area is very dependent on a very broad range of theory. And at this workshop, we're lucky to have leaders in all of these areas here, and you'll hear from several of them in the coming days. So now I'll shift to focusing on some next generation tools, the things people are working on in the field to keep pushing it forward. Generally, these the sensitivity to new physics, the sensitivity of these experiments scales as some product of intrinsic sensitivity, meaning how amplified are these effects in the molecules, how big are the internal fields, that sort of thing. How long can you coherently probe them? And then the square root of the count rate. And so I'm going to discuss how molecular experiments can combine significant enhancements in all of these areas, which can lead to orders of magnitude improvement for a very wide range of beyond standard model physics, not just for CP violation, which is what I'll focus on, but dark matter, parity violation, new forces, exploring weakly coupled sectors. So pretty broad impact. And these experiments and theory will benefit from concurrent advances in other areas. So in particular, quantum information science, which has a lot of the same basic requirements for what these experiments that I'm going to talk about need, which is just you need to be able to coherently control complicated quantum objects. There's been a lot of advances in that area. And also access to short-lived and exotic nuclei, which is something that I'll talk about later, which can give dramatic enhancements of intrinsic sensitivity, especially to CP violation. So one of these areas is laser cooling. The motivation is that beam experiments, including the most sensitive EDM experiment with thorium oxide, the ACME experiment, also the ytterbium fluoride experiment, they use molecular beams and they're limited by time of flight to a few milliseconds. So the beam passes through some detection region, processes, and is read out. You can extend this coherence time by, for example, slowing and compressing the beam, which you can use with lasers or with other methods. But if you can trap the species, you could get orders of magnitude improvement. You could go from milliseconds to seconds, possibly even many seconds. This long coherence time from trapping is an important ingredient in the hafnium fluoride plus and the radium atomic EDM experiments that have shown this. This really is a good path forward. For neutral species, at least, they must be ultra cold, meaning less than around 1 millikelvin, simply because the types of traps that are suitable for these measurements for neutral species are very shallow. So the species has to be very cold to begin with. And laser cooling is a very powerful technique to implement to reach those temperatures. Lasers are, these days routinely used to cool atomic gases to microkelvin or even sub-microkelvin temperatures, which is a major driver of the large portions of the AMO and quantum information science fields, and it's extremely advanced. So people can do highly sophisticated things with laser-cooled atoms these days. In order to realize laser cooling, you generally have to cycle around 10 to the 5 or so photons. So you need to add up the momentum kick of around 10 to the 5 photons to, say, take some typical thermal species and cool it down to an ultra-cold temperature and trap it. Some molecules can be directly laser cooled, although even the simplest molecules that have a laser coolable structure are still really complicated and it's still very, very challenging. So molecular laser cooling is still a frontier. The first laser cooled and trapped molecule was only in 2014. Since then, a number of other diatomic and later I'll talk about polyatomic species have been laser cooled. Another avenue, which I'll revisit briefly later, is that you can also assemble molecules from ultra-cold atoms. So start with ultra-cold atoms and then coherently associate them into ultra-cold molecules, which works for species that you can make out of pairs of ultra-cold atoms. And this field is advancing very rapidly, driven largely by the quantum information science and precision measurement goals. We're excited to pursue, and a lot of other people are excited to pursue this avenue, because if you take some numbers, each of which can be realized in some system, all of these combined are yet to be realized. But at least this seems like a realistic vision of an experiment. So you had 1 million molecules in some optical trap with a 10-second coherence time, and it was some heavy molecule with good sensitivity to CP violation. And you run it for just 1 week. If you run through those numbers, you'd find that you'd be accessing new physics at the 1000 TeV scale or so for generic CP violating physics. So this is an opportunity to explore really high energy scales, which I'm excited about. And there are a number of experiments that are pursuing this approach. One is ytterbium fluoride. So that same beam experiment, turns out ytterbium fluoride has a laser coolable structure. And they've demonstrated laser cooling and are working on implementing it into their experiment. Barium fluoride, which the NLEEDM collaboration is working on, which wants to combine laser cooling with advanced deceleration techniques, which they've had some exciting results about recently. And thallium fluoride, the Centrex collaboration. So they're not looking for an electron EDM, they're looking for the thallium nuclear shift moment, which is sensitive to, among other things, the proton EDM. And I'll talk about some other laser cooling experiments later on as well. All of these experiments and several of the other ones I'll talk about later start with a step called buffer gas cooling. All of these molecules are free radicals. They're very chemically reactive. They have high melting points, so it's hard to just even get them in the gas phase in the first place. And so they all start with this technique of using a cryogenic buffer gas. You take a cold, few Kelvin copper small chamber, a few centimeters by a few centimeters. You fill it with usually helium gas or maybe neon. You inject the hot molecules, usually through ablation of a solid precursor. those hot molecules thermalize. So you get a gas of cold molecules. They don't react with the helium or neon. And if there's some hole in this cell, you can create a beam and then direct that beam toward your experiment. And it's a very powerful and flexible technique. It works, you know, in quotes, it works for anything. It works for atoms. It works for large, complex organic molecules, and can create, and everything in between, and can create cold flow and high flux beams that are a really important ingredient in ACME and all these laser cooling experiments. So another avenue of research is using polyatomic molecules. The general motivation is that if you allow yourself flexibility in what you stick on some metal, you can engineer interesting properties with these ligands. For example, you can control the magnetic and electric field interactions. You can engineer very highly polarizable systems. You can stick, if there's some species of interest you want to study in here, like if you're interested in studying the oxygen or the carbon or something, you can stick that in a laser coolable species. You can adjust the frequencies of vibration and rotation to match to some physics or engineering that you're interested in, and so on. And if you are careful about how you choose this ligand, you can also preserve the desirable properties of this other species. So for example, if this is some laser coolable metal center in calcium fluoride, there's a number of other things you can replace the fluoride with and still get something that's laser coolable, including, you know, this or even, you know, surprisingly large complex organic molecules. Well, this is a schematic. People have been looking at photon cycling and laser cooling and things that are essentially this large and complicated now these days. And if you do proper quantum chemical calculations, you find that basically the electronic part of the wave function is really localized on this metal atom. It doesn't depend so much on what's over here, at least for a large class. And so you can preserve laser cooling if this was some intrinsically sensitive heavy species for CP violation searches. That's generally preserved as well. There's lots of other interesting things you can do with polyatomic molecules. I'll point you toward this review if you'd like to learn more. So 3 examples, again, of polyatomic precision measurements going on. One is YBOH. So this is something that I'm involved with John Doyle, Tim Steinley, and Amar Vutha to combine laser cooling and high polarizability in polyatomic species. You can use the polyatomic structure to engineer magnetic field interactions in a very favorable way for parity violation searches. You also hear a talk on Thursday about this, not on polyatomic molecules, but using the same general idea of using magnetic fields to dramatically amplify parity violation searches. Polyatomic molecules offer some unique prospects for that. Radium containing polyatomic molecules, which combine some interesting properties of the radium nucleus with ion trapping. Molecules like this have already been created and controlled. There are other interesting, not polyatomic molecules such as protactinium fluoride 3+, which was recently proposed and explored, and more. This is just a selection, but I'll talk more about these 2 just because these are the things that I know something about, and I'll give you sort of an update kind of what we've been working on, at least for some of these, and our collaborators have been working on. So even one of the challenges of working with these polyatomics is just because they're not as explored. Even doing some of the basic steps are not so clear. So in my lab, we've been focusing on things like implementing optically enhanced chemical production to make very high yields of these molecules in a cryogenic environment. Last year, we used this method to come up with a new approach to interpret dense and overlap spectra, which is a characteristic of these very complex molecules. And our poly-EDM collaborators combined very high precision and accuracy theory and experiment to look at these branching ratios important for photon cycling very carefully. The things we're doing at Caltech these days, in the last couple months toward these ends, implementing coherent spin precession, so seeing the molecules coherently interacting with external fields, implementing photon cycling in all the isotopologues to do the different experiments that we want to do in the lab, including the odd isotopes, where the photon cycling is very complicated by hyperfine structure, and doing high resolution spectroscopy, in particular of the science state, which show a portion of the spectrum below that we recently measured and assigned. So another area that's seeing a lot of exciting stuff going on is in using deformed nuclei, which give very large enhancements for hadronic CP violation. Quadrupole and octupole deformed nuclei can significantly enhance hadronic CP violation, so CP violation arising from within the nucleus, so things like theta QCD, chromo-EDMs, nucleon EDMs, CP violating nuclear forces. These are interesting because they combine with the molecular enhancements that I mentioned before. The quadrupole, in quadrupole deformed nuclei, you can get large enhancements of magnetic quadrupole moments. You get collective enhancements in the nuclei, which for heavy species is typically about an order of magnitude. Quadrupole deformed nuclei are not that hard to find, so there are a lot of good candidates for species with large quadrupole deformations, including 173, which we work with in my lab, 173 YBOH for a nuclear magnetic quadrupole experiment. Octupole deformed nuclei can have dramatically enhanced nuclear shift moments by 100 or 1,000 or in some cases even more. These nuclei are a little harder to find. Heavy and spinful end octupole deformed nuclei are short-lived, and there just aren't that many of them, but there are still some very interesting candidates like radium, actinium, thorium, and more. These can combine with these molecular enhancements to give 10 to the 5, 10 to the 6, even more intrinsic sensitivity gain for hadronic CP violation versus, say, atoms with spherical nuclei. Of course, on the other hand, these atomic experiments like mercury and xenon, radium are extremely advanced experiments. So they're really hard to beat, even with these dramatic enhancements. But there's a lot of hope that going forward, as the molecular technology continues to improve, that these experiments could lead to big improvements. But also remember, we actually need multiple experiments in multiple systems anyway to get robust limits and properly interpret the results of the experiments. Just as a side note, truly exotic nuclei like protactinium, which I mentioned earlier, could offer an additional factor of 100 to 1,000, maybe, but there are some nuclear structure questions that need to be answered. Radium is especially interesting for a number of reasons, but maybe the biggest ones relevant for this are the atom, the ion, and several molecules of radium can be laser cooled because it has a very simple electronic structure. The nucleus has been studied quite carefully and has this octupole deformation. And so it presents a venue to combine basically all of these things I've been talking about: laser cooling, polyatomics, ion trapping, deformed nuclei. So there's a lot of interest in radium, including many ongoing things. So radium is the subject of an EDM experiment at Argonne National Labs. Radium fluoride, there's this recent exciting spectroscopy on, and there's been more since then as well. And it has this laser coolable structure. But there's a lot of other species as well: radium ion clocks, radium assembled ultra-cold molecules, trapped polyatomics, laser coolable neutrals. So there's a lot of cool things going on with radium. One that I know more about is these radium polyatomic ions, where you can take the radium atom and you can sort of engineer and choose the ligand that you attach to it to match your experimental needs. So, for example, in these ion trap experiments, the measurement protocols are fairly dependent on the details of the molecular structure. And you might need different details depending on how exactly you want to do, what sort of measurement you want to do. There are different protocols and proposals on how to do these CP violation searches in trapped ions, spin precession or quantum logic spectroscopy, or using clock transitions. You need different structure for all of those. And so in my lab, we've been exploring theoretically what these different, how you can engineer these different structures by attaching different things to radium. And these, so these are 3 examples, all of which have been created in Andrew Jayach's lab at UCSB that we in our lab explored theoretically by doing things just like looking at the structure of these molecules, calculating the sensitivity to nuclear shift moments and the magnetic moments, and making sure that they have the right structure and features that you need to actually do these experiments. Because you can combine these very sensitive nuclei with these very large enhancements from the molecule, the intrinsic sensitivity is so high that even if you can only trap one molecule at a time, you could probe the frontiers of hadronic symmetry violation using this approach and other approaches using radium with long coherence times. So to close, I'll just briefly mention a few other directions. There's many things in this area that I haven't gotten to talk about even at all, but I'll just mention a few more. There are ongoing efforts at JILA and other places to implement next generation ion trapping. So taking the JILA type EDM approach and really scaling it up very dramatically in a way that would work for a wide variety of CP violating physics. So keep the long coherence time, but add really high count rates. Assembling ultra cold molecules, including heavy deformed nuclei like francium or radium, with turns out silver is a good partner, although this is all theory at this so far. And trapping species in noble gas matrices, so freeze molecules or atoms in something like argon ice, which could give extremely high densities and count rates and surprisingly high coherence times. And so this would be potentially suitable for a pretty wide range of species, including rare isotopes. This might be an easier way to work with very short-lived isotopes. So in conclusion, I'll thank my group for doing the work that I showed and acknowledge our many great collaborators and funding agencies that support our work. And thank you for your attention.
Thank you, Nick, for a very nice talk. So yeah, we have time for a few questions. So I can start, Nick. So for the polyatomic molecules that you are investigating in your lab, YBOH. So now that you have the experiments, how does it compare with the theoretical predictions? So can you say that we have a good theoretical understanding of those, or any surprises?
Yeah. So actually, maybe I don't have. Yeah, I don't think I have the structure on here. So there is. Well, here you go. This is a good one. So this diagram. Well, actually, this is a generic diagram, but I think this is actually for SROH. For the most part, there were not any surprises. But there were a few, including some important ones. And I think one which we're still investigating is that you can see that, for this theory, at least the experiment and the theory agree to, pretty small fractions. But these experiments are now getting to the point where you really, in order to reliably scatter, 10 to the 4, 10 to the 5 photons, you have to know these things, even at this point, to theory, to levels that you just can't calculate with theory. You just have to go and measure them. One surprise, which we're still sort of fully trying to understand, which was seen with both YBF and YBOH, is that they have inner F-shell excitations that these excited electronic states can decay through. The branching is very small. It's so small that it's hard to know what it is, even theoretically or experimentally. But it's large enough that it can't be ignored. And so nailing that down and characterizing that is something that's ongoing, both with YBOH and with YBF. So that was I think that was kind of the only surprise. Other than that, we've started doing this science state spectroscopy. That state had previously not been observed, but there had been some, great theory work along with some just like back of the envelope stuff that I did. And while that is still ongoing, it looks like that state looks exactly like we predicted.
Okay, sounds good. Yeah, thank you, Nick.
Thank you so much for the invitation. And today we'll talk about various applications of atomic theory and some of the recent advances which happened in the past couple of years. So first, there are many different reasons why you want precision atomic data. So of course, development of atomic clocks, various experiments with ultra-cooled atom, quantum formation, quantum simulation, astrophysics, plasma physics, particle physics, searches for dark matter and other new physics, and of course, the topic of this conference, extracting various nuclear properties from atomic spectroscopy. And today we'll talk mostly extracting of nuclear properties, specifically how to extract precision nuclear moments. And I will talk a little bit about the search for dark matter because those two topics are actually very, very highly related. So first, where is dark matter? Well, we expected that it's all around us. So our galaxy is really supposed to be completely embedded in this huge sphere of dark matter, which is much, much larger than our actually visible galaxies. And the point is that all those stars which we see in our beautiful sky, there's only 0.5% of the matter energy content of our universe. And this, then the rest, of course, it's gas and mostly hydrogen and helium. And then our dark matter is supposed to be 85% of all matter, and then there is dark energy. So from our current picture of our dark matter distribution, that mostly it's Sun and Earth going around our galactic center, and essentially the dark matter wind is blowing in our hair, so there's should be plenty of the dark matter to detect. The issue here is that unless we actually think that dark matter particles solve some other kind of physics problems, a hierarchy problem, the strong CP problem, we actually have no idea what the dark matter mass is. And if we don't have any other ideas about what those dark matter particles should do, except, interact gravitationally, then our limits for the dark matter mass are actually very poor. So on the left-hand side, we have about 10 to the minus, 21 sort of EV based on galactic structure observations. And on the other side, we essentially not limited by anything except the Planck mass, because at that point, your particle just becomes a black hole. And at this point, there are very many different, of course, experiments to look for those dark matter in all the possible scales. But if you think about quantum sensors, they're actually interested at the dark matter somewhere less than 1 electron volt. Why? Well, because at that point, dark matter becomes coherent at the scale of our detectors. And specifically for atomic and molecular and future nuclear clocks, we are talking, if we're comparing clock to clock, somewhere under about 10 to the minus 12-ish electron volt. If we're comparing to clock to cavity, we can expand it, or cavity to cavity, to a few orders of magnitude more. So why dark matter? Why the clocks specifically would be sensitive to dark matter, and how the nuclear physics, of course, is related to all of this topic? Well, the first thing which we do know about the dark matter, if it's light. So if dark matter is lighter than 10 electron volts, then it has to be bosonic in our galaxy, because if it's lighter than 10 electron volts, if you just compute what the Fermi velocity is, it's going to be higher than galactic escape velocity. So this dark matter, if it's fermionic, it really couldn't exist in our galaxy. It couldn't make the galaxy form, and it would have left by now. So in this case, what happens if the dark matter is light? Then you ask yourself the question, how many particles do we actually get per de Broglie volume? And in this case, we find that we actually have dealing with very large occupational numbers. And if you're dealing with large occupational numbers per de Broglie volume, Therefore, you can say that our dark matter, in this case, we can classify dark matter whether it's a scalar, pseudoscalar, vector. It will exhibit coherence, and it behaves essentially like a cosine wave. And here at the mass, it's a mass of our dark matter. So periodicity, therefore, depends on the mass, and therefore the corresponding Compton wavelengths of the dark matter. And here is the basic idea. The reason why clocks and various other quantum sensors will be sensitive to such dark matter, it's because it's coherent on a time scale in the space scale of our detectors. So how would it work? How would you actually search for dark matter with clocks and atomic clocks, future nuclear clocks? So the basic logic here, so your dark matter field would couple electromagnetic interaction with normal matter. Why? Well, because if the dark matter only talks gravitationally to your standard model particles, then it will have to produce gravitationally. So in principle, this is possible, but fairly difficult. So we assume the dark matter has some other interactions. And in this case, even if you don't know at all what the dark matter is, we still, assuming the basis spin statistics, it has to couple, and based on our, of course, normal rules of how we can, of field theory, that we actually know how it should couple to normal matter. If it's a scalar, then you simply take your field and multiply it by your standard model Lagrangian, or you take a square of the field. So it's a simple linear coupling. So therefore, you take your dark matter oscillating field, you multiply it to all the terms of our normal Lagrangian, and what happens? Well, you just added oscillating component to everything in your standard model. Therefore, every coupling constant which is in front of your Lagrangian term, every mass which is in front of your Dirac term will oscillate. So all of the fundamental constants, all of the masses, therefore will acquire small oscillation components. And this oscillation signal, it's what our dark matter signal is. How would we see it? Well, if fundamental constants oscillate, if mass ratios oscillate, therefore the energy levels, which are all depend on the Rydberg constant, therefore in atoms, would also oscillate. And therefore your frequencies of all your clocks, atomic clocks, molecular clocks, nuclear clocks, because clocks essentially is just the differences between two energy levels, they will also oscillate. Okay, how do we detect it? The main concept here is that the level of the oscillations, the level of sensitivity to those effects depend on what energy level you have. So for example, light atoms are fairly insensitive to it, and heavy atoms are more sensitive to it. Why? Because essentially we're looking at relativistic effects. We're looking at effects which are beyond the normal alpha squared, where alpha is a fine structure constant. Therefore, what you do, you take two different clocks, either with sensitivities to the plus and minus signs, or one is zero sensitivity and one is high sensitivity, and then you monitor clock ratios of clock frequencies for, well, as long as you can. And this is essentially what metrology institutes do. They do compare clocks, they monitor ratios of frequencies for a long time. Some of those experiments actually date back 10, 15 years at this point. And of course, the next thing which we do, we would like to find the clock, find the transitions which have the highest possible sensitivity to those effects, because that essentially gives us the largest chance to detect dark matter. And here now we come to the nuclear physics and to the nuclear clocks. So all of the currently operating atomic clocks, and those are fantastic devices. They won't lose 1 second in more than a lifetime of the universe. All of those fantastic clocks, they're based on transitions in atoms. So they started from the transitions in the microwave region, and now they move to transition optical spectrum, because this is allows you to build more accurate clocks. So why atoms? Why not nuclei? And unfortunately, I don't have time to talk about molecular clocks. There was this fantastic presentation which you just heard about molecules. Yes, also the molecular transitions are sensitive to dark matter, and more, or they're also sensitive to different couplings of dark matter comparing to normal atomic transitions. So that's also very interesting topics. But now, why not nuclei? And the reason why nuclei is because for the clock to work, you need to be able to laser excite your transition, and just simply there are no lasers for nuclear transitions. Because if you look at the typical nuclear transitions, They are in a keV to MeV range that's way outside of your high precision tabletop lasers, which are limited by, you know, a few electron volts. So if you look here, all those red dots, those are the energies of typical atoms which are used in clocks. And as you see, they're all under 10 electron volts. So surprisingly, there is one exception. There is one nuclei, thorium-229, which has a low-lying isomer. So it's actually about 8 electron volt transition. And as of now, that's the only candidate for nuclear clock. The next best one, I think it's 889 electron volts, is still quite far away. And in this case, this is essentially an accident. In this case, the transition wavelength, it's about 150 nanometers with about a few nanometers, about 3 nanometers uncertainty. Lifetime is projected to be about 5,000 seconds. It's, as of now, experimentally, it's definitely more than 60 seconds. So it's already good enough for a precision clock. In fact, if it's 1,000 rather than 10,000 seconds, it's actually better. And there are now several projects around the world to build such a nuclear clock. And you either base it on a single ion, on thorium 3+, because thorium 3+ is good because it's like francium. There's only one valence electron. It's pretty much the way most of those current ion clock work. You have either 1 or 2 valence electrons. Those are very controllable systems. You can actually laser cool thorium 3+ directly. And this is one of the projected accuracy of such clock would be about 10 to the minus 19. Or you can actually build a solid state clock when you embed the thorium-229 into the solid state matrix. And that's a completely new idea of building clocks. And the review and the plan of the ERC Synergy project is has recently actually been published last year, if you're interested. So why a nuclear clock would be good for dark matter searches for variation of alpha, searches for violation equivalence principle? Well, it's because we expect that just because of this accident of nature, you have a very interesting scaling in the system. So we already know the transition at somewhere like 8 electron volt. But then the sensitivity to variation of fine structure constant, what does it actually depend on? And that depends on the difference of the Coulomb energies between the ground state and the isomer. And the Coulomb energy itself is somebody like 10 to the 9 electron volt. It's a GeV scale. So we presume that those cancel to about MeV. I will show you the latest idea of what the numbers actually are. But unfortunately, this cannot be calculated from nuclear theory. So, and if you just use this hand-waving argument that the cancellation about at MeV scale, so you divide 8 eV by MeV and you have about 10 to the 5 enhancement. So the idea is that here you have enhancement of the effect at about 10 to the 5. So what does it mean? It means that if you build a clock with 10 to the minus 18 precision, with the precision of the current best atomic clock, that your sensitivity for the dark matter and alpha variation is actually 10 to the minus 23. So you actually have for free 5 extra orders of magnitude. So you don't have to build 5 extra orders of magnitude more accurate clock. You can just build 10 to the minus 18 clock, but you actually have so much more chance of seeing dark matter. So all your sensitivity curves essentially shifts down by 5 orders of magnitude. Of course, the important question is, what is action enhancement? And unlike the cases of parity violation ADM, you don't actually need to know action enhancement. It actually does not come in into any extraction of dark matter. It actually only comes to the limit of the dark matter. So the larger the factor is, the high chance actually if your detection. And there had been a proposal by Beringwood, Zuboff, Landau, and Porsev of how to actually extract the sensitivity without actually trying to calculate it directly. And the basic idea is where could the difference in Coulomb energy come from? And from a very simple ideas that will come from a differences between the nuclei in the ground state and an isomer state. And that will come from the isomeric radii, so the difference in the charge radii in the ground isomeric state, and the difference in the quadrupole moments. And as of now, the isomeric radii actually had been measured, so this ratio is known actually well, but the ratio of the quadrupole moments is still not known with required precision, so we still actually don't know what the enhancement is. But it has been projected, if you relate those to quantities, has been projected being about 10 to the 4 at this time. And the project to actually make much more precision measurement in a precision ion trap of the ratios of the quadrupole moment is currently underway. And that brings us to the question of nuclear moments. And as I showed in the very initial slide, you need atomic theory to extract those precision moments, not the ratios, but actual moments. So back in 2013, we collaborated with Alex Kuzmich group to extract the value of electric quadrupole and magnetic dipole nuclear moments of thorium. It's a for ground state of thorium. And we found that actually those actually were quite different coming from atomic spectroscopy than for the previous older value. And of course, they're actually quite different from the attempts to compute those from nuclear physics as well. So the question is, can we do better? And with advancement in atomic theory, which happened in the past few years, the answer is yes. So what we have actually done in 2013, we've done, and I'll explain in a moment what it is linearized couple cluster computation with single, double, and partial triples. And we also have done some additional fitting based on a barium plus. So it was not fully ab initio calculation at that time. So a little bit about the couple cluster method. We are now computing properties of thorium 3+. And why? I mean, technically, you can extract nuclear moments from thorium, from neutral thorium, from 2+, 35+, from anything. But 3+ is very good because that's where you can do the most precision calculation. Why? It's because in thorium 3+, you have only a single valence electron, and everything else, all the other electrons can be described by essentially mean field. And the idea of the couple cluster method is that you have a cluster operator which acts on your lowest order Hartree-Fock wave function. And then you expand this cluster operator in terms of excitations, a single excitation, double excitation, triple excitation. In a simple linearized case, you're actually very easy to see what those excitations are. So you simply take one electron in the core and excite it to any possible excited states. Essentially, you have the sum over all possible bases here. Or you can take a valence electron and you do again excitation to all possible excited states. And then the double excitations are the same thing. You can either take 2 core electrons, excite to excited states, or you take 1 core electron and 1 valence electron, and then you excite those to all possible excited states. That's a very basic idea of the couple cluster method in terms of excitations. And of course, you can do 3, 4 more excitations. As you see, of course, with thorium 3+, you have a lot of electrons to excite. The beautiful thing about couple cluster method, that generally single and double excitations are the largest, and then triples are smaller, and the other side technically as expected to be smaller. So, and then what we've done previously, we actually first reduced it to only single, double, and triple excitations, and we dropped all nonlinear terms, and then out of the dropped all the core terms for triples, and out of the valence triples, we took only perturbative terms, a very small subset of perturbative terms. And then we used some empirical fit afterwards in 2013. And now I'm happy to report we have a full single, double, actually, and full triple code. In fact, actually, sorry, it's not VT. We actually, beyond VT, we actually have now a full CCSDT code. And in this case, the difference between VT and the actually full CCSDT is that instead of just having 2 excitations from the valence and 1 excitation, 2 excitations from the core and 1 valence, you actually have also 3 electrons excited directly from the core. And that's a new part which has been added. In the valence, we added actually completely, and also we can actually have full numerical inclusion, meaning we don't actually have additional numerical restrictions in the valence part. And we looked first at barium plus, and we found in barium plus that if you really want to do a sub% computation, a core excitation have to be included. So, and that is the first results of the full CCSDT code. So the only thing which we don't have nonlinear triples, but we have all nonlinear single and doubles. And these are actually pretty small. And this code this new version been written by Sergei Porsev. And as you see, the precision of the removal energies of thorium 3+ are now 0.3%. More than that, we actually see convergence of different methods. So here's what we had before, LCCSD, and that is about a sort of, 1.5% difference. Then actually, if you add all the linear terms, you have a reduced difference with energy. So there's a difference with the experiment. If you add the valence triple, that you actually half the difference. And if you add now quarter triples, you actually improve even further. And if you look at actually energy computed, calculated from the ground state, you can see that now we actually have just a few inverse centimeter differences for those cases. So this is the most precise computation which ever been done for thorium 3+. So what happened with hyperfine constants? Now we do all those things for hyperfine constants, and for hyperfine constants, we also have corrections to the operator, which is a whole other different thing that's all been computed as well. We also done basis set extrapolations to actually, already starting with a large basis set, we extrapolated to essentially infinity. And in this case, we find that our uncertainty is under 1%. But then, of course, we remember that this is not the whole story. The whole story is that to compute hyperfine constants, you have to remember that you need to know what the magnetization is. And honestly, we don't know what magnetization is. No one knows what the magnetization is for thorium. So generally, we start with a uniform magnetization. And then what we did, we use experimental data in order to actually extract from theory what's the difference between a uniform magnetization and the true results. And we've taken the difference with experiment then is an uncertainty. And we find now that at this time, the main uncertainty in our case comes from Bohr-Weisskopf effect. So it no longer actually comes from theory anymore. It really comes of determination of what the correction is. So how do you resolve it? So what we need at this point, we essentially need better experimental data. And we need better experimental data for several different levels. In fact, it would be great if we could actually have experimental data for S levels, because those actually have very different dependence for Bohr-Weisskopf effect. And, and that would allow to improve the precision further. And the method which I just described, that actually will work for any nuclei when you can actually do the experiment with only one valence electron if you remove enough electrons here. So in principle, there is many different cases which we can compute for which this method will actually work. For the electric quadrupole hyperfine constants, we actually now have projected better than 1% precision, significantly improving the results which we had before. Interestingly, the actual numbers pretty much did not change. We actually, within the uncertainty which we defined as out of 13, it just uncertainty got smaller. And then the next question, what do you do then now if you have more than one valence electron? And in this case, let's forget about how many valence electrons you have. In any case, in any number of electrons, the method which called configuration interaction will work. So in this case, the idea of the method is very simple. So you simply take your wave function and say, this is a weighted sum of all possible configurations. So you take your electron and you put them in all possible combinations, and this is your sum. The way it actually works, so this is your configuration. Your configuration, it's your slated determinant, which has a combination of all one electron functions. And generally, with the basis set function, well, you can have anywhere, say, 50 to 500 basis set functions, depending on what that actually you want to do. And it sounds great. The problem that the scaling is exponential. So if you say have 150, which is kind of intermediate number of configurations, in this case, this scales as a number of your basis set functions to the number of your valence electrons. And clearly it becomes unmanageable very quickly. The thing which rescues us is that technically the same logic applies as is for the Kappa cluster. The single and double excitations are the ones which are the most important. The question is, you have to decide which is important and which is not without actually making serious errors. And what turns out to be that it doesn't matter actually, even if you find a perfect set, if you actually construct your configuration space and you know that all of those are important, we found that for many valence electron systems, you end up with a very, very large number of configurations. So the question is, how do you solve this very, very large problem? And now this is a computational problem, and we started with a serial code, and we now have a parallel code with the MPI and dynamic memory allocation and scalable to actually thousands of the CPUs. And this is one advance which allows us to compute much, much larger systems with configuration interaction. And just to make an example, that was our first test which we run, Iridium 17 Plus, because also that's been proposed for the clock. So the serial code which ran 2 weeks will run in 15 minutes with our current resources. And here is the scalability. Again, we have to construct the matrix, and then we have to solve the matrix, find lowest eigenvalues. So here is number of nodes. Each node has 64 CPUs. So in the scaling is with number of nodes, not cores. So in the end, we actually had 2,000 of the CPU working on this problem. And as you see, we started with about 10 GB of memory per core, and now it's 2 GB memory per core. So the scalability of matrix construction is perfect. It's essentially 100% scalable. Solution Davidson actually is much, much harder to parallelize. So as of now, our factor, it's at about 70% level for the total code, up to about 2,000 cores. But again, what we've done took 2 weeks, now takes 15 minutes, which means we can run much, much, much larger problems. And here's one example. Here is actually one of the suggestions of how to excite the thorium transition, suggested by Adriana Palfi's group and collaborators. And the idea here is to actually tear more electrons from thorium. Thorium 35 plus has a very accidental degeneracy of the electronic transition versus the nuclear transition. And the idea is you excite this transition, then the electronic decay of this transition gives energy to your nuclei and allows to actually excite the ground state as a merit state, which then you can actually look for the decay. And in this case, this is called an electronic bridge, and its efficiency depends on just how close do you get to the nuclear state. And we carried out a CI computation, and in this case, we had actually all of those electrons, so for P shell open, for D shell open, and for F shell open. So all of those electrons, as you see, it is a 25 electron CI, with a fairly moderate set, but we actually found that we did converge it with a basis set, and we find that after opening the 4p shell, the numbers pretty much stopped changing, and we actually could put error bars on those numbers, and we did find that this transition is even closer to the nuclear transition that was expected. In fact, now actually the next question is what exactly the nuclear transition energy is. So as soon as this is actually measured to high precision, we know exactly what the efficiency of this excitation is. And in this case, this is a 120 million determinant run. And the next step actually in developing of methods will be also to have neural networks select the configurations as well. And just in the end, I would say that those two methods are also combined. So if we have under 6 valence electrons, we can actually combine the kappa cluster with the configuration interaction, and all of the valence interactions are run by the CI and everything else run by kappa cluster. And this is a new example. That's a very first and yet unpublished test of this approach to 6 valence electrons. This is uranium plus result. This is uranium results. And as you can see, the energy is actually a fantastic agreement with experiment here. We also now proceeding, we are almost done with the computation of the hyperfine constants and seeing if we can actually improve on the uranium nuclear magnetic moment as well. And this is a beautiful work done by Sergei Porsev, and this will be submitted for publication shortly. So to summarize, how do we classify our difficulties of atomic theory computation? So we can classify the group 1. For the group 1, it's 1, 2, 3 valence electron that we can do routinely. So in this case, the codes can be turned into software. Group 2, 4, 6 valence electron, we can still do high precision computation as I've just shown. And generally, the computation of wave functions still requires expert knowledge, but everything else actually it's very straightforward. And then for the sort of a mid part of the periodic table, half-filled shells and holes and shells, that method development is in progress. And therefore, I think it's time to see if you can actually compute everything in the periodic table, to boldly go when no one goes before, to automate the codes for massive data generation and make them all available. That's our new portal project. So you can go, it's just udel.edu/atom. That's already available online. And right now it contains 25 elements, including some highly charged ions. The version 2 just been released. Version 3 will be released shortly. It will contain more, much larger number of elements. And then we're actually going to release all of our linearized kappa cluster codes, and then eventually the CI code, the parallel CI code as well. And we have also many ideas of what else you can do, the ideas for the light shift simulator, the ideas for interface, which actually allows you to search for an atom and ion specific properties. and then full automation of all the codes and portal interface as well. And if during the discussion, if you're interested, I can actually show you the portal and how that works. And for now, I would like to thank our portal team, our group at the University of Delaware, and our collaborators. And thank you for your attention.
Thank you very much, Mariana, for this very nice talk. So, questions? Yeah, I can start with one. Well, Gordon, yeah, please start.
Oh, yeah. Thank you, Mariana, for a very interesting talk. I didn't quite understand how the coupling with the dark matter would cause oscillations in the fundamental constants. Are you assuming some kind of coherent oscillation? Why doesn't it just average out? And what would the frequency be?
Okay, so let's go back here. So I didn't show the coupling of the Lagrangian. So in principle, I can, let me see, explain here.
I guess it's the question of coherence. Okay. Why doesn't it average out?
Okay, so first, because the dark matter can be so on the scale of our detector, and for the masses which you look at about if you. So the first question, why there is an effect and what the frequency would be. So your coupling is you simply multiply this field to your F menu term of the Lagrangian. So that's the answer to the first question as to why actually there's oscillating effect and what is the frequency. So the frequency is, it's the Compton frequency of your dark matter. So it's oscillating at the Compton frequency of your dark matter. So essentially alpha now has an oscillating component. And the next question, why doesn't it average? And eventually it actually is going to average. And that depends, and that's actually what places the limit of how sensitive the clocks are. So when the clock operates, what you do, you first put the clock in superposition of your two states, and then you wait. And the question is, how many dark matter oscillations do we have during the wait time? If you have more than one, yes, then it actually starts averaging. But there is actually a special what's called dynamic decoupling sequence. If you start applying the pi pulses, which rotates your essentially your clock state during your probe time, you can actually extract the signal without losing those dark matter oscillations. Yes, if you have too many of them, that yes, you will start averaging, and then actually you will lose signal at about 10 to the minus 18 if you just compare 10 minus 12 if you compare clock to clock. So it's honestly the question of the scale. And then, of course, if you have less than one dark matter oscillation, so what you do, you have the time series of your measurements, you do Fourier transform, and now you essentially have your frequency signal. And that frequency signal is at Compton frequency of your dark matter. So it's a very specific signal. But you're right. So that's why the clock sensitivity eventually drops, just because the oscillation becomes too fast. But then you can actually compare the cavity, because cavity response is proportional to alpha, not alpha squared. And that allows you to sensitivity actually for higher masses.
Yeah, I hadn't thought of that before. It's very interesting.
Thank you. Some more questions? So I can ask my question. So, well, Leonid, please go ahead and I will get my turn for the last. Yeah.
Okay, so my question is about the method to measure the transition frequency in thorium nucleus. So you showed a picture where one have resonance between nuclear transition and atomic transition, and the transition energies are quite close. But my question is, do they close enough? So I do not see exact resonance, but maybe it is not important.
Okay, first, this is just one of the proposals to measure it. So you definitely don't need to use it. So there are several different things which actually people do right now to measure this frequency. So this is one of the proposals when it could be the probably easiest to actually make the excitation. So there are three different ways. So the first way actually has nothing to do with, so the first way to actually make so the way the energy measurements are done right now, it's actually not by laser excitation. People try to do that, but they haven't seen it yet. So in fact, the neutral thorium actually is fairly short-lived because there is an internal conversion process. So what actually comes out, not a photon, but the electron. and they measure actually the energy of that electron. So that's right now how the energy is being measured. So as soon as you actually get it to better precision, then what you can do, you can simply take thorium 3+, or you can take actually what they do normally, they actually embed thorium into the solid state matrix, into the crystal. And then you shine your laser at approximately the right frequency, and you see if you actually see the laser light coming, you see the light coming out. So this one, but the idea is that in certain cases, when you have electronic transition which is closed, it's going to be enhanced. And how enhanced it actually matter, it really we don't know, because it's very heavily dependent on actual difference. So, but honestly, I think this is a very nice scheme. And because there is now a new effort with highly charged ions, it's called highly charged ions, this is one of the possible schemes. But in principle, you don't really need it to excite. You just need then be closer to the excitation to excite. So in principle, there are numerous searches throughout the world which simply just have the laser near this frequency and just scan the laser and they shine it in the thorium crystal. So, but here, if it turns out to be, then it's, in principle, this method would allow you to pinpoint the excitation better, because then the probability of excitation will very heavily depend on the energy. But of course, you need to actually have cold thorium 35+, which still, that's, you know, a bit challenging as well. But this is not necessary to actually make a nuclear clock. You, in principle, already there are frequency comps, which at approximately the right frequency, and there are also gigahertz lasers, which are approximately the right frequency. All you need to do is just spend enough time scanning the frequency. But the plan is actually right now, it's to improve it using the electron methods, using the internal conversion. But then as soon as you do by about factor of 5 better than you know right now, to actually use laser excitation. But a number of groups already proceeding with laser excitation as well. So, and then to building the clocks, you just need to build better and better lasers and pinpoint frequency better and better.
Thank you.
Good. So yeah, I think with this we can end this session and officially move into the discussions. So I will keep my question for the discussions. So now we are open to have questions for all presentations, all during the day and yesterday. So, and I can start with my question, Mariana. So you put in question mark, what do we need? And one thing that our community needs from atomic theory is this field shift and mass shift calculation. So more specifically, mass shift, precise mass shift calculation. So can you say a bit about that?
Right, so we actually, so the CI code is set up to do both mass shift and field shift calculation. A couple cluster code right now is set up to do field shift calculation because it's a one-body operator. It can be done straightforwardly. So we actually have done this calculation for thorium ions. So, and that had been published. So we extracted the RMS radii differences. In this case, so the issue here is that field shift we can actually compute very precisely. The mass shift, that's a whole different question. So right now, that means that where the mass shift is a few percent, our precision is sufficient to extract the total isotope shift, to extract the radii with a small error because error on field shift is small. With the mass shift, as I said, we do have this working. This is now part of the code, but essentially it's very hard to determine independently what the precision of that is. For the lighter systems, I think for the highly charged ions, the precision could be actually much higher, of course. The reason being because mass shift operator, it's a two-body operator, so you can't really compute it directly as the expectation value. We have tried before, and this did not actually yield the results we wanted. So we now actually compute it as also correction to the energy. And I have to say that we have not spent sufficient time on analyzing the results because we only were interested in the heavy elements, and we just wanted to calculate the mass shift correction with maybe like 3% of the total. So in principle, method exists. I think for the King's plot, for the light elements, for the highly charged ions, it could be done precisely. For the neutrals, that's a good question of how precisely calculate the mass shift. So, and I think the field shift, on the other hand, the precision is very good. In fact, we actually have field shift results now for ultrabeam plus as well, and we actually have interesting project also related to dark matter searches there. But the mass shift, its correlation corrections to mass shift are very large. So I think computing the accurate computation of the mass shift and demonstration of accurate computation of mass shift, it's a complicated question which we have not fully explored. So essentially we need a whole new project to explore this. But nevertheless, as I said, the code runs. So what we do, we just have, we'll scan the energies with essentially different mass shift and take the derivative. So that is set up.
Thank you. There are two cases where we specifically need help, urgent help: aluminum mass shifts and silicon mass shifts, neutral both.
As I said, that's that'll be interesting project. I guess the question is just whether the numbers and different approximations will be stable or not. And as of now, we try to do that directly with a couple cluster. And we did not achieve agreements. We tried actually with Vladimir Duba, and we done it different methods. We actually have paper published long time ago, and we got pretty different results. We tried to actually use potassium and rubidium because there's enough node data to try to actually extract what the kind of experimental specific mass shift is, and we couldn't reproduce those data. So but that was baked maybe like mid-2000s. So we haven't tried with a new method.
Good. Yeah, thank you.